The clarity of the water is determined by measuring water turbidity. The turbidity meter measures the density of particles in the water, including organic matter. Our turbidity meter sends a beam of light through the vial, and the amount of reflected light reaching the turbidity meter sensor provides the turbidity reading, measured in nephelometric turbidity units, or NTUs. The higher the turbidity reading, the less clear the water is. When the water is visibly brown, the turbidity reading is likely to be higher than normal readings for that particular site. Highly turbid water poses a danger to corals by limiting light availability and reducing photosynthesis by symbiotic zooxanthellae, the primary source of nutrition for many corals. The amount of salt in the water is determined by the salinity measurement. Salinity values in the ocean water are expected to be around 35 parts per thousand, or ppts. When reading the salinity values, you should expect them to be within a range of 34 to 36 ppt. If the salinity value is below 34 ppt, it could indicate freshwater incursion from streams or submarine ground discharge, or SGD. Evaluate your surroundings and past weather conditions to help determine why the salinity may be lower than the normal range. Note that when submarine ground discharge is present, its greatest effect may be around low tide. Not all sites have streams nearby or SGD flow, but it pays to know which sites do have these inputs. These sites should be listed on your field data sheets in the notes section and in the freshwater outflow guide document in the field binder.
The relative acidity of the water is determined by measuring pH. If pH is high, it indicates that the water is more basic. If pH is low, it indicates that the water is more acidic. Some factors that influence the acidity of water include ocean acidification from increased carbon dioxide in the air and coastal acidification from excess nutrient inputs. Our pH values are expected to lie between 8 and 8.3. Sometimes the values will be lower than 8, especially at sites where there's little wave action or the site is protected from waves by offshore reefs or an embayment. pH levels in the ocean are important because high acid water with more CO2 reduces the availability of carbonate ions that reef-building corals need to protect their skeleton. The amount of dissolved oxygen in the water collected is measured with the oxygen probe. If there's a lot of wave action, dissolved oxygen values in seawater tend to be higher. If the water is still or stagnant, the dissolved oxygen levels are often lower. How much oxygen the water can hold depends upon seawater's salinity and temperature. The level of dissolved oxygen in seawater is important because if oxygen values are too low, aquatic organism survival can be impacted. Oxygen dissolves more readily in cold water and when the salinity is lower. The nutrient samples we collect during sampling days are sent to an analytical lab for processing. The parameters that are measured include levels of total nitrogen, nitrate, nitrite, nitrogen, ammonium nitrogen, total phosphorus, phosphates, and silicates. Nutrient information is important because it can help us identify sites that may have excessive amounts of these nutrients. While nutrients are important to the health of the reef, in excess, they can be a problem. High nutrient levels can indicate that a site may have pollutants from agriculture or sewage entering the ocean through runoff or submarine ground discharge, or SGD, from upslope sources. In excess, these nutrients can cause an overgrowth of algae that blocks sunlight and consumes oxygen that corals need for respiration.